Okay, we are here in the fall of 2021, and this is the fourth lecture. And it has a couple of words that, well, I don't see associated very much, and I'm a fan of both of them. The first word is uncertainty. Now, up to now, we've talked about models and time, and everything was totally predictable. The Newtonian approach tells you if you know where you are here with infinite certainty, you know how you'll get there, etc., etc. Then we started talking about risk, but all we talked about really was risk factors, things that can influence your perception of risk. But risk itself is inextricably tied with uncertainty. Without uncertainty, there really is no risk, because the whole future is predictable, and the entire past, you can rewind it using your equations. So if you forgot, you just go back and you just calculate where you were. Okay. So this is the first lecture where I'm going to try to tie these things together. The Laplace domain, we're all very familiar with. I called it here the Laplace domain, but we've been calling it the discount domain. In any case, originally Laplace only one real number. And later on, engineers and complex analysis guys extended that to complex numbers, so they folded the Fourier transform. So this is still in the spirit of, yes?
I think the microphone on you just turned off because I hear you less well. I still hear you, but I think I hear you.
Yeah, I did turn off. So maybe the battery is gone. Yeah, it probably was empty already. Dat word ik voor betaald. Ze hebben net een grote promotie gegeven om nog meer te praten. Oké, ja. Dus kan je nagaan. Kan je nagaan. Hè? Dus maak je borst maar nat. Anyway. Where were we? The Laplace domain. Now, one of the things that I find often is things that are very natural in economics, although we have this analog between economics and engineering, and sometimes you have these things that are totally natural in economics, the use of the Laplace transform itself or the exponential function, that are not so natural in engineering, and vice versa. And this is one of these one of the subjects where this is going to be quite natural when we think of economics, and something that I, at least, have not seen done very much in engineering. I've seen it used with the Fourier transform. I've seen uncertainty used a lot with time domain, you know, witness the Kalman filter and all this. You guys get entire courses on that, right? But in the Laplace domain, not so much, okay? So this is at once the most exciting thing, I think, of economic engineering, that you kind of see, you know, now even your own engineering things, you can look at it from a very different light and make progress in both fronts. Okay. The other reason I love uncertainty is because my old specialty within control was stochastic control. This is where I did my PhD thesis in at the time. This is where I was a professor in, and this kind of stuff, and building probability models. Now, the idea I had was that, well, let me go back. When you usually use uncertainty, and that's still the case now, usually it's just sprinkled in on as if it were pepper or salt that you put on food. So first you make your whole model, your Kalman filter, and you say, hey, I have some noise. So here, let's put some noise in here and some noise in here. What's the distribution? You know what? Let's take it to be a Gaussian, you know? And somebody says, well, is that the case? You said, no, I don't know whether it is the case, but it seems to be. And you mumble something about the central limit theorem if you're really pressed. And then if you're otherwise pressed, you would say, well, it's very mathematically tractable that way. Okay? And then because of mathematical tractability, we do it. Okay? Now, I hate that. Right? So I hate that for two reasons. So the not so important reason is I think, well, this is engineering. It's not mathematics. What has it got to do with anything, you know? But then you might say, well, of course, more research is needed to figure out what the real distributions are, and we're going to look at different distributions. So, but what I really don't like about it. When you say something is mathematically tractable, you really mean in view of other mathematical assumptions that you've made, okay? So a phase lag is very mathematical tractable if you assume that there's something follows a sine wave, okay? But if you have a square function, a phase lag is going to be mathematically very untractable. Okay, you may have to view it in the complex numbers and get your phase lag in there. So all of a sudden, it becomes mathematically intractable. So mathematical tractability is always, you know, an indication that somewhere in there, you've already assumed the type of model that has a certain structure that makes this thing end up to be mathematical tractable. Now, in economics, like a lot of this other stuff in engineering, what happens when they do stochastics, they always have some kind of regression model. And what is a regression model? You just have this point cloud, and you start fitting it to a line or fitting it to something else. So get the line that is the closest. And when they mean the closest, they mean, well, you draw it on the blackboard. At that time, they still had blackboards. Maybe you can draw it on the whiteboard. But anyway, I start measuring the distance of this data point to my line and that data point to a line. And then they say, what do you mean by distance? Well, I just put the ruler there. Now, what's the length of that ruler? Well, that's sum of squares, right? Okay, that's how we measure distance. So you use the Euclidean distance. So then you get all these sums of squares in there because that is what you call close. So you end up with a distribution that's got sums of squares in there, okay? And yeah, there are not so many, and one of them is the Gaussian, and it has some other properties, that it's stable. If you add lots of them, you remain within the Gaussian family, etc. Okay? So in there is always this assumption that you know what close is, and that closeness is just putting a ruler on whatever you draw on the blackboard. But as you draw it on a log scale, there will be quite different. There will be squares of logs, which are certainly not squares of other things. Okay? So we're going to take a very different approach here. We're going to, we are in good shape, you see, because we just don't have point clouds, we got models, okay? So with these models, we have a certain structure, you know? So we know that certain things, you know, this thing has to, if it's there, then it's got to go over there. And if it's there, it has to go over there. And with the structure comes a sort of symmetry. If you have a harmonic oscillator in the faceplate, it's invariant on the circles. You can really just turn it around. And so with a torque, it doesn't really matter what coordinates you take for x and y. What really matters is the distance and the angle. And if you turn it around, I mean, that's not going to change the energy or the angular momentum or torques or anything. Okay? So there are certain symmetries implied by the physical laws. And what we want here is to have distributions that obey those symmetries, that don't go against it. And they will end up to be the ones that are correctly encapsulating the notion of randomness, especially random time or something like that, or a random frequency, okay? And then when we calculate with them, we can recover what distributions these things obey, and then we can also do parametric inference and Bayesian statistics and all of that. So that's the journey I want to take you on. So distributions are not going to come from the sky. We're going to carefully derive them with the structure we have here. All right. That was also the topic of my PhD thesis, and I guess that's why my academic career got started at that time, because nobody ever looked at it from that point of view. You know, that you look at the physical laws and say, can I derive from that what probability densities will govern the phenomena? And I derived in my thesis, I think, the normal distribution exponential, a bunch of things. Okay. So this is the first time that I can actually put together these two kind of sides of me. So I actually know a little bit about this stuff, although my knowledge is a little bit dated, probably. But some of it you'll be surprised is almost the same problem. Huh? Anyway, let's get going. So before I do this, I need to talk. I noticed that when I was preparing this lecture, that I had omitted to talk about second-order systems and second-order returns. You know, we all did these single pole things and etc. So in order to find out the structure of the S domain, we need to talk a little bit about this, not very much. A lot of things you already know, but we need to talk a little bit about this because then it will be obvious what we mean by a random discount rate. You know, right now with one pole, it's not so obvious. It's almost obvious, but here it becomes really obvious. So let's make a small excursion to something that you all know and love, the regular second order system, right? So here is a time domain response, and this is the frequency domain, right? So you can just have a damped harmonic oscillator, and second order system with damping. You'll get something like this with a sine wave, all right? And you do some, you do a Laplace transform, you know you have a second order equation, right? Because you got a mass, right? So you got your second order effect, you got a damper. It's the first order effect, you got a spring, the 0th order. So you got a second order system, and you just write down here the characteristic equation, you'll see it, right? Now, these things you all recognize. This is the natural frequency, right? K over M. This is the damping, what do you call this? The damping ratio or the damping factor? Damping ratio, I think, right?
Zeta.
Zeta, right? So this is the damping ratio, I believe, right? Huh? It's actually it's B divided by 2M, if I recall correct. No? Oh, sorry. B divided by M is equal to, B divided by M is 2 zeta omega n, right? And omega n is K over M square root. Huh? So I bring this one down there, and I wiggle this one around, and then I get the right expression, right? Huh? Whatever. Huh? I don't say whatever. This is important, and I don't want you making these kind of mistakes. The point is, you know what it is, all right? And why do they choose this thing? Well, the zeta is kind of important in the sense that it very much determines the character of the solution. So when zeta is 0, you have no damping. This term falls away, and this thing falls away. You just got a sinusoid, right? Okay? And as you crank up zeta, the thing starts acting more as a sinusoid like this, right? Okay, until zeta is 1, and then it's critically damped. And why is it critically damped? Because if you see, if I plug in 1 here, the whole sine part disappears, and I'll just get this thing. Huh? So it looks like an exponential, almost. Right? There's a little bit of an initial value for the velocity. You have to take care of that, and then, you know, all right? And then you bring it up even further. The damping ratio. You're on the overdamped regime. So what happens then? Anybody knows?
Argument.
Yeah, well, that's already quite advanced because that's I wrote here. But normally, how would you solve that, right? So you have this characteristic equation. You start looking for the poles, right? Huh? And then you'll find a complex conjugate pair, or you find a repeated pole, right? Or you find 2 real poles, right? So if you have these systems where you crank up the gain on the feedback loop or whatever, the poles start over here, and then you circle down like this, right? This is a root locus, huh? And then one pole shoots off this way, and the other pole shoots off that way, right? As you increase the damping ratio, right? Huh? So this will be a situation where zeta is bigger than 1, right? And you get these 2 poles. Huh? So you get 2 real poles, and normally they'll write a solution like that with 2 e to the minus this, and, you know, 2 exponentials, you know. Something like that. Huh? Okay. So Emil was already being clever, you know, but this is kind of always been a curious fact, right? So when it's underdamped, you have this nice conjugate pair, you know, then it's critically damped. You kind of see what happens. It's just, they're still conjugate. They just happen to lie on top of each other, right? And then when it's overdamped, they kind of just go, oh, okay, well, now this whole conjugacy is lost. Huh? All right? So there's a bit of a problem because this is exactly what we're interested in as economic engineers, that discounting. So I wanted to put this back in there. And let me do that before I talk to you about the economic interpretation, all right? So I want to put this back in there. So Emil already suggested multiply, the problem with zeta is bigger than 1, then this thing becomes smaller than 0, right? The square root will become imaginary, right? So you got a problem because now you got the sign of an imaginary number, right? So you got the sign of some imaginary number I times else, right? Actually, this thing. Now, what is the sign of an imaginary, right? Now, a lot of people will go blank at this point, but actually it's the sinh, right? Okay, the hyperbolic thing. It's easy to prove. I just don't want to do it now. It's easy to see graphically. I also don't want to do it now. I'll do this some other day. And it's in connection very much with Emil's stuff, where you move from compound interest to simple interest to this, what he's been calling circular interest, where you move through this all of a sudden to the sinh, and you see this hyperbola emerging. So I refer to his work if you really want to understand that, but it's just a fact. You can just look it up. So I can rewrite this thing like that, all right? So that's interesting, right? So, okay, fine. Now, let's have a look at this. So I got this picture, and then in the last minute, I noticed this is about the cosh, but it doesn't make a difference. I just add a phase lag, and I'm okay, right? It's just that I wanted to take a picture from the internet to show you that I'm not monkeying around. So here you have a picture of this critical jump system. You see, apart from some little bit, this will look kind of like an exponential. This one is damn sinusoids. And here is something that's where zeta is equal to 2. Now, what's happening here, right? Now, you would first think that this is exponential. And if you look here, for most of this thing, it's going to look just like an exponential decay, right? So you'll be fooled into thinking, if you take a close look, and you'll see on the internet lots of guys who just plot it as an exponential, but it's not. You'll see here, it definitely isn't, right? Because an exponential, it will, the derivative will be proportional to this, to where you are, right? And that's not happening here. The thing is like moving off, all right? So what's happening, if you look at the formula, what's happening with this cosh thing is there are really two exponentials. There's one on a very short time scale that apparently goes very slow, and one on the long time scale that goes very fast. You see that? And the formula will just tell you that. If you look at it, you see two exponentials, one with a very short, very fast decay, and the other with a very slow decay, right? So first you see this one happening, and then you see that one happening. Okay, that's what's going on. Now, why would you do that? Well, what's the economic meaning of that? All right? Why would you do that? Well, we've all been thinking of discounting or something. I do it with the discount rate, and that's just what it is, and I get an exponential discount. Why would you do this? What would be a reason if you just think of yourself, right? Suppose that you're a student at the TU Delft, right? That's not hard to imagine for most of you, and you're deciding whether you want to go for the long run and do a really great thesis your first years, or you just want to party. Now, the party is today, and the thesis is 6 years from now. You may decide to kind of party, all right? So that means that the near future is way more important to you than the far future. So you're discounting the near future much slower than the far future, all right? So there's some kind of cutoff point where you say, all right, this is so far, I don't even care anymore, all right? And that is what goes on here. That system, that overdamped system, goes with two rates. At first, it discounts kind of slow, and then it discounts really fast. And economists call this also hyperbolic discounting. Now, if you read their thing, it's unclear to me why they call it hyperbolic discounting. But what's nice is that you see indeed, these type of expressions, the hyperbolic function, showing up to describe this. All right? So what an economist will say, if you're a drug addict or something like that, what you have is that your immediate wants, if I think of it as a want, will dominate kind of, are more important than the future wants, okay? So here you discount really slow, and here you discount really fast. And they have noticed that that's how people are, and the argument is usually that that's wrong. You shouldn't do that, all right? And you can make money, and there's hedge funds who are based on this idea that people do that and that they want. Now, what I think is, my personal opinion is they're not wrong. This is just what they want. I can imagine if you don't have that long to live, you may want to do this. You may want to say, all right, they give me, 3 more months to live, and then I'm going to have fun, and then let the future, take care of itself, But if you have a business, the business has this infinite lifespan, so the business, like a bank, can offer a constant discount rate because it's there for, all the shareholders, and the shareholders don't die. The shares just stay, okay? So it's a way you can do a profitable trade between very large businesses and individuals, depending on, what is your lifetime span, okay? Well, there's nothing wrong with this. And of course there's nothing wrong with this, because you are just a second-order system. You're overdamped. If you are, then we all know you're minimizing your expected cost, and this is the equation that does it. The Euler-Lagrange will just tell you this is the case. It's optimal. So to go around and say this is not optimal, you can do that in economics, but you cannot do it in economic engineering, because that's just the result of your assumptions, okay? All right. Now, this is the concept of hyperbolic discounting. It's very interesting. A thesis has been written here in this group on this by Edward Swetham, and he explored this and compared it to the economic literature. And it was very nice thesis. And a very interesting topic, like what's the relationship between overdamped second-order systems and what they call hyperbolic discounting. Anyway, that's not our topic of today to say how nice this all is. It's just to give you that interpretation of what's going on here, okay? So in the frequency domain, how does this look in the discount domain? So here I call it contraction. I prefer to call it this hyperbolic discounting, but whatever, right? So what you do is you look at the characteristic equation, and I just set that equal to 0, and those are the poles, right? We all know that. Here you are. And then I'm going to find out what those two exponentials are. Now, if you solve that, you see that this is what you get, right? So if zeta is 1, you get your two, well, this is not the, well, this is the S-plane, And then you see these two poles, one here and one here, all right? And then shooting off depending on what zeta is, all right? So these are these two values of the exponential, right? I'll call this pole 1, e to the minus pole 1, t plus, b plus b times e to the power pole 2p, right? These are two poles, okay? And we know that they go like this, all right? Now, how does that look on the Riemann sphere? Now, on the Riemann sphere, everything becomes clear, right? We all know that. So here they are. So here I drew just the, this is the real axis. This is just the sigma axis, right, of your S variable. This is not the omega axis. This is just the Riemann sphere north-south pole, all right? So that's this axis plus another axis where I put infinity there. And then I just take whatever the pole was here and project it on the Riemann sphere by stereographic projection. So this pole goes over there, and this pole goes over there. All right? Clear? So what do we see? All of a sudden, when these poles go to 0 on this, what we see is this thing is just moving to infinity, and this thing is moving to 0 here, right? And they are still conjugate, but instead of drawing the conjugate like we do in the I omega sigma plane like that, I now have this kind of Riemann sphere picture with this other axis, but I still draw that bar to indicate what the conjugate pole is. So this will be the one belonging to the plus, and this one would be the one belonging to the minus, I suppose. Right? Huh? Okay. So this is a very, everybody's nodding, this is a very pretty picture. It solves this whole issue of what's happening at infinity. Well, that's exactly what's happening at 0. I mean, the thing is just symmetric in this way. So you see that the slow eigenvalue and the fast one, you know, they are just conjugate to one another in this picture. So in a certain sense, what happens is, although this distance from here to there, if you just use a measuring rod, looks humongous, right? And the distance from here to here looks just 1, because this is the point 1, over omega n, I should say. Huh? Okay. It really isn't. They're just the same thing. And if we were just, instead of thinking that we live in the S-plane, realize that we live on the Riemann sphere, we wouldn't have all these issues, and we'll just say, all right, we're just going to the North Pole. I mean, seriously, right? Okay? And the trip from critically damped to a pole at infinity is the same as a trip from critically damped to a pole at 0. I mean, seriously, because if you flip the thing around, you look at 1 divided by the transfer function, you'll get an output and an input, and then you just, and that's just flipping the Riemann sphere. So the whole symmetry of output to input, input to output is just built in this way. Okay? Now, that's neat, right? I mean, and you may think, if you really like this, like, well, wow, I wish they would have told me that when I was drawing these root loci, because this is just much easier. I just draw them on the Riemann sphere and imagine myself a little boat just moving around. It's a really great picture for a Dutchman, because we get educated, and that's what our forefathers did, and now I'm doing the same, but I'm going with a pole, right? Huh? All right. Okay. But I want to make a different point here. So this I did kind of fast. So you can give lectures on this, but I don't want to do that now. I just want to make this one point. From this point of view, you see, the distance from here to there is the same as the distance from there to there, right? So if I would say, where is a random pole, a random IRR, or a random discount rate at which this thing diverges, what would I say? Would I say, well, it's distributed uniformly on this line? Certainly not. It's ridiculous, right? Because then this thing would never be conjugate with that thing, that pole, because this thing has the chances of being equal chance to be at an infinity, and it can't be. So what I would have to do to be reasonable at all is assume that it's uniform on the Riemann sphere itself, all right? So green is probability. I just have somehow, there's an axis coming out of the board, I suppose, like a uniform distribution on this thing, right? And then maybe I can extend it for growth to that thing, okay? That's what I have to imagine. So if I take a ship on the Earth at a random location, or an airplane, what do? Do I take the map of the world, and just put a random point? No, of course not, because it was way more likely that I'll be at the pole, because I got the poles all stretched out in my usually Mercator projection, okay? This is ridiculous. It's not so likely they're at the pole if they're at an unknown location. What you would do is to say, well, they can be anywhere on the surface of the globe, these airplanes, and both, of course, can on the North Pole or on land. But in an airplane, you could imagine there's no such limitation, or a satellite. Could be anywhere, not on the projection, on a map. All right? So the point I'm making here for probability is an important one. Your knowledge that the S domain has the structure of the extended complex plane, is enough. So you need that in order to talk about the uncertainty about the S parameter. Okay? Why? Because this is the only way to make sense of what you call randomness. If I take a random location, that's what it's got to be. I got to go to the globe. I got to take a random location there, right? Okay? So, now, nobody does it that way, right? So everybody puts distributions on the real line, okay? And this is the problem, because what is a uniform distribution on a real line? It doesn't exist, because you would integrate 1 from minus infinity to plus infinity, you get infinity, and there's no way to normalize that to get a probability density. So they immediately run into trouble. So they immediately have to assume some type of distribution that at least converges when you integrate it, like the Gaussian or the normal distribution. All right? But we have no such problem, because we know that the infinity that we draw on that piece of paper is just not a figment of the imagination, but it's just a coincidence of the particular projection that we're using on a flat plane. Okay, and the true structure is that of the Riemann sphere, and that is what we need to do to choose a probability distribution. All right? Okay. So, everybody with me here? Any questions about this? No, and we will we'll leave this topic. I think it's a very interesting topic, by the way. Analyze the motion of the harmonic oscillator, especially from the perspective of the Riemann sphere, and then look at what has got to do with economic engineering. And Emil is currently already quite deep into this. So we'll hear much more about it. But it's not my intention here for this lecture to do that. For some reason, I don't know what happened. I lost the... here we go. So here I went ahead and actually did this, all right? So what happens, so here I have that same Riemann sphere. I just changed the opacity a bit. The thing receded to the background, I'm just projecting in the same way, all right? And I just put a uniform probability density function on the Riemann sphere. So I just use this azimuth. I think azimuth, I always get them confused, but this is probably azimuth, right? Sometimes they use the zenith angle, which is this one, but I think that will also work. But let's just take the azimuth. Huh? That's another nice thing of the Riemann sphere, by the way. What people typically do, and I like it, is to use the same terminology you use for, geography, right? Which is the origin of geometry, is the way of measuring lengths on the Earth, right? That's really what we're doing here. It's geometry, it's the origin of geometry. Okay. Huh? Yeah, but I want an angle, huh? And it's not latitude. You see, the latitude is spaced evenly here, right? Huh? Oh, yeah, right. So you don't want that, because you want the angle because it's uniform on this thing, right? Huh? So this is d theta. So you want that f theta. So f is a probability density. D theta, that's your little bit of probability, right? And that is uniform. So they're the same. For all theta, huh? Okay, yep. That's what this means, that this is a constant. Huh? And it's easy to figure out what the constant is. It's the 1 divided by the circumference of the circle, right? 1 divided by 2 pi, all right? Well, that's, the 1 divided by 2 pi should be yawn, okay? Like, okay, why pi? Okay, thank you. It just so happens that you have a sphere. What should not be yawn is why that silly number pi appears in the normal distribution or other distribution. That does seem to come out of nowhere, right? And you do this whole integration, you find that it's pi. Say, what is it? And then you have a lot of people, and they're more philosophically inclined than they are inclined to figure out what's really going on. they'll call it a magic number pi, and it shows up all over the place. But if you look closely, it only shows up because he's got some geometry of the circle built into his whole thing. Okay? So then the mystery disappeared, but of course he sells less books. And he needs cleverer people to look at it because they have to understand what's really going on. So it's not good business. So that's what I did. And then what you can imagine doing is projecting that out, right? So you'll see that if I have a little bit of probability here, then I got to project that out. So this thing goes over there, and that thing goes over there. So it gets a little bit stretched out, right? So if I have it here, or down here somewhere, right, went off, then it looks like perfectly flat, right? Are you guys cool with that? And then as you go to infinity, the thing gets stretched out infinitely, so the tail looks very thin, all right? Nevertheless, this is called a fat tail distribution, right? But you'll see, that was pretty clear, right, what's going on. Formally, what you do, well, if you want to look at f of s, it's f of theta times d theta, and this will be f of s times ds, so you'll do this. And this will be then the Jacobian of the transformation, right? I just calculate what the Jacobian is, and you know it's a tangent, right? So I look at this theta tangent of this thing, and blah, blah, right? And I can figure it out. But I don't like this so much, right? I mean, I like that you can do this, but I like to see that you can just eyeball it and know this has got to be right. Got to be right, okay? Just intuitive. All right? Now let me ask you some other questions about this. What's the probability mass that you find from 0 to 1? Anybody has an idea? A quarter, yeah. Now why is that the case? Yeah, you take a quarter of the circle, it projects that down. So what is the probability mass between here and there? It's a half, right? Right? So the Cauchy distribution is a distribution that does really well with what they call quantiles. So if you want to know where a quarter of the probability mass is, what you do is you find a piece that contains a quarter of the Riemann sphere, you project it down, and you're done, right? Huh? So the Riemann, the Cauchy distribution, it's called a Cauchy distribution. All right? Huh? It will tell you it's a unique distribution that has half of its probability mass between +1 and -1. All right? Easy to see, right? What's the mass of all this stuff? Also a quarter, right? So yeah, you can, and this quarter is a fractile. This is when you look at everything to this side or everything to this side. That's what they call a fractile, all right? So you can plug a quarter in here, and then you do by times pi, and then tangent. You'll figure out, you can just calculate this formula by you know, like that, right? I'm not going to do it for you, but you can see that, right? Huh? This is the tangent, of course, right? Huh? Or the derivative of the tangent. Well, that's easy. Huh? What's the mode of this distribution? You know what a mode is? This is where it's the highest. So it's right in the middle, right? Why is that the case? Well, it's obvious. Like this thing is parallel to here, so you're going to get most probability mass just kind of pumped down, right? Projected down. Everybody else is stretching it. So, you know, you're going to have a peak here, and it's going to go down. All right? Okay? So, you know the mode, and you know, what do they call this in statistics? The probable value, and that's where half of the probability mass is between 0 and +1, right? You can rattle off a lot of statistics. You can rattle off another one. What's the expected value of this here? You know what the expected value is, right? Huh? So you just take S, multiply it by. What is that? And you say 0, right? Why?
Because yeah, it's symmetric
Yeah.
both sides. So then
Yeah, so it will be 0. Everybody agrees with that? Either people have no opinion or, huh? Ozai is looking stern, huh? He is not sure. Why are you not sure, Ozai? Huh? What's the only other thing? Huh? That can be the.
I don't see it that quickly.
Right, so his argument is, well, the expected value should be here because it's equally likely to be there as to be there, right? So if I calculate this integral, minus infinity to 0 is going to be the same, so therefore it's got to be there. That's his argument, right? That's what most people think, right? But it's wrong. Yeah, it's wrong. So what's the only other option that this thing can have? This thing can do it, huh? If it's not there. Well, yeah, it doesn't exist, right? It doesn't exist, yeah. Infinity, you can call it infinity, but infinity is right here. How can it be there, right? Huh? So it doesn't exist. Yeah, if you calculate it, it doesn't exist. Just plug it in. You will see that if you do this, and you integrate, you'll get something that looks like a log, right? 1 over s. This diverges. Huh? So that's considered something weird of the Cauchy distribution. And you know, the problem is, look, if you calculate s times this, it's what we call a fat-tailed distribution. So there's enough probability mass here at big S's that you multiply with a big number that the thing never gets hit down, right? Huh? Well, it just keeps adding moment, you know, like the moment, this is the moment, the expected value, and you're just calculating S times whatever this probability mass is, right? And you're hoping this thing S times the probability mass is going to go down to, is going to, you know, going so far down to 0 that if I add it up from then on, it doesn't explode in your face, okay? But that doesn't happen here, okay? So certainly if the distribution would go down with this exponentially, it will happen, right? That's what the normal distribution. And it has very thin tails, okay? It's pretty useless for statistics because the tails are too thin, so they get all this black swan events, all right? Okay. So the Cauchy doesn't have an expected value. It also doesn't have a variance, of course not. Right? If you multiply by s, and you can't integrate, multiply by s squared, it's not going to work. Absolutely not. Now that's the mathematical argument. What's the economic argument or the physical argument? If you just knew the Riemann sphere. Suppose you forgot about the fact that you have this S line and this, and you just had this normal distribution on this circle. It's just the Earth. And I'm asking you, where do you expect this guy to be? I mean, it's ridiculous. That's why King Arthur's knights had the round table. There is no preferred location where you expect one of these knights to go sit. Okay? So the distribution has no expected value because that's what you built in. That's what the circle builds in. If it was a square, certainly. You know? If it was an ellipse, even then you'd be in business. Okay, but the circle just happens to be that thing where the Knights of the Round Table was sitting on precisely because it has no expected value, right? Everybody is equal. I mean, it should come as no surprise. It's ridiculous to calculate it. Where do you expect that plane to be then? Okay, then you don't have a uniform distribution, my friend. All right? Now, the whole mystery of the Cauchy distribution that you calculate, and there's papers devoted to this, is really, from our perspective, just that's what we mean to say that we have a random frequency or a random discount rate, that there is no expected value of this thing, right? What's the problem, right? Okay. Usually that's taken as the reason why you should not take a Cauchy but a Gaussian, okay? And then they find out this was actually a big problem with the crash in 2008, that there are all these events, and there's a guy who made a whole career out of it called Nassim Taleb, or Taleb, I don't know how to pronounce it, right? And who went around and wrote a book, I think it's called Black Swans, you know, the book. And it's about all these events that happen in the tails, okay? And they underpredict all of them. So later, when they said how risky these things were, it turned out that all the stuff that was never going to happen did happen, all right? So all kinds of stuff that was supposed to not happen is happening all the time. This is a problem in Wall Street, you know? So they're just using the wrong distribution, okay? Now he goes around and says, you can't use these techniques and people don't have a good answer. My answer will be, no, you got to know what you're doing. Of course you can use techniques, but but it's a raging debate. You can look this up, okay? But this is just to get you comfy with the Cauchy distribution, right? Now, I'm going to get you guys way comfortable with this thing, all right? We're going to go explore it, and we're going to look at value at risk from this perspective. We're going to look at all kinds of stuff, and then we're going to do Bayesian inference on it. And I'm hoping to cram this all in this one lecture, all right? So, we'll go on. You guys are all with me. Yeah, right? You're still awake. So, all right. So now let's say, okay, we have this distribution on S of a discount rate, but that's not really what we're interested in, right? We're interested in the distribution of the value of what we have, right? Our portfolio or our whatever, right? Or the return that we're making, which would be a transfer function, or the loss, which would be a loss function. But let me now just look at this value, right? So it's just the probability distribution on the Laplace transform, right? Now, the picture is just, in principle, so simple. You know you have a distribution on S, and you know you have a function of S that you call the value, evaluated at this discount rate. Now, if you have a PDF on a variable f, you'll have a PDF on this function. There's no doubt about that, unless it's not differentiable, right? But we don't worry about that kind of stuff, all right? Right? You just have to calculate what it is. Well, what is the density function? It is just a density function on the discount rate times this Jacobian of the map, right? You learn this all in probability 101. You remember this or not? Why is this the case? Because what you need is the probability of seeing V, dV, as a function of S. I can write it like that. Has to be equal to F. Yes, right? So the probabilities have to be equal, you know? So when S happens, then V evaluated at S happens, right? So the probability that S happens is the same as the probability that the value at S times the change in the value. This is just what's going to happen. Divide by V, right? And probability is positive. Sometimes these things go negative. You put absolute value sign. But if you keep your head screwed all right, this always goes right. Okay? Simple. So why is it so simple conceptually? Because we did all the hard work. We already know. We spent a whole lecture, I think 2 lectures, to deriving what this value should be. There's just a Laplace transform. Then we started looking at the losses. This is the next slide. But the point is, as soon as we have a distribution on the discount rate, we can calculate what the probability distribution or the uncertainty should be on everything that depends on that discount rate, namely the value, the risk, and a whole list of stuff, right? In principle, okay? In principle. Now, this is this connection we're going to explore, and we'll see that just because of the way we chose the Cauchy, that it has extremely nice properties. And this is not because I'm so brilliant in choosing a distribution with all these properties. So this is the typical, maybe, mathematician's approach. You first list all the properties you want, and then you go prove what function does it. We just say we have this physical or economic situation. Now, then randomness is this. And reasonable things we do with it, we should have some reasonable, reasonable answer that we can guess even. All right. So, okay, let's let's just, kind of loosen up a little bit by doing a few things. So first of all, let's look at the function 1 over s. Now, remind me and remind everybody, what does this represent? What, huh? Do you remember? Yeah, but I don't want that. I want an economic meaning, right? Huh? It's the value of perpetuity, right? Huh? Okay. So when you look at this stuff, I asked this for a purpose. I want you to keep in mind that this is a, a totally legitimate function of s, right? So we know what the discount rate is, and we want to see how much a perpetuity, we know what the probability or uncertainty of the discount rate, and we want to see what is the uncertainty associated with the perpetuity, right? Right? Super reasonable. Not only super reasonable, that's the first thing we really want to know. Huh? All right. Now, if you know a distribution of some variable, what's the distribution of the inverse? Huh? You know that? In general? That's going to be difficult. I mean, most people go blank then. Like, oh, damn, I got to look this up, right? You got to look it up. And then, so something is normally distributed. What's the distribution of the inverse of that thing? Do you know that? I don't. I have to look it up. I think it's called an inverse normal distribution. You don't know? Huh? It's not so obvious. And why not? Because this Jacobian here is going to suck a little bit, I think it's, you know what? I know what it is. It's sort of a bi-sided chi-square distribution, but whatever. Huh? Okay. Huh? So, but now what's the inverse? This is Cauchy. What's now the inverse of a Cauchy, right? Now, you can go into the literature, you'll find it's also a Cauchy, right? So the Cauchy distribution is invariant under inversion. This is a very special distribution of this. I don't think I know of any other. Huh? There may be some. And then there are going to be mixtures of Cauchys. Huh?
Be any distribution that.
So what is A1 over S? Right?
Right?
Yeah, you flip it, right? That's what I want to do. So this is the distribution of S. What's the distribution of 1 over S? 1 over S is just flipping the Riemann sphere, right? Infinity goes to 0. And how does the uniform distribution look on the sphere, on the flips? Yeah, and then you project it down, what are you going to get? And you're going to get the same thing, right? Well, something that looks totally mysterious and ridiculous. All of a sudden, I know how the values of a perpetuity are distributed. Is super yawn, and I mean, why are you bothering me with this, right? Now, suppose you had launched yourself into a derivation. You probably would have made a couple of mistakes if you're me, because I can't get these things ever right. Huh? And you would have considered it a total mystery, right? But all I did was just flip it around, right? Yeah, boom. Huh? Okay. So it's the same. Well, that's important for us because remember the other lectures, we looked at all these different functions. This was an important one, right? We've got some other important ones. The other one is something like this. So we write things like 1 divided S plus A, or you multiply this by B, I don't know what, right? So what you do is you take this thing and multiply it, I call it gamma mu, and then you can first do this and then do that, right? So you see with a couple of these results, you sit and you diddle around, right? And you can get the other result, okay? So what's going to happen there? Well, I chose these Greek letters for this because in statistics, that's very standard, is to take an observation and use a Roman letter. So these are things you can really observe, and take what they call parameters and call them, and they assign Greek letters to those. But these are statistical parameters, and these are called what they call samples. Huh? This is the S for sample rather than the S for frequency for this moment, right? You can think of it as a sample, all right? Okay, but V of S is also a sample because this is a function of that. We'll talk about measurable function and integrable over Borel sets, but that's all irrelevant, okay? Because we are dealing with Laplace transforms, and these are pretty well behaved, so you can just do any old silly integral, okay? So when you read these texts, don't get too imposed by knowing all this measure theory, all right? So the question is, what is that? Now, we know that too, because remember, we were doing these transformations of the Riemann sphere, and we were shifting them and moving them. I think I omitted to say what happens when you multiply. So if you have a price that's not equal to 1, for instance, right? We'll see this also shows up as duration. But you remember you have an impulse, and it's 1, and then you multiply it by some price. But you can also take a perpetuity, you multiply it by some number gamma, and then instead of the coupon being 1, the coupon will be gamma, right? Okay? All right? So how do you get that on the Riemann sphere, these gammas? They are, now these multipliers. Now the way you do it is you move the Riemann sphere over from the plane, okay? You lift it up, and then you project it. So what happens if you lift this thing up and you project it? Well, I drew this here. So here is the old location. So 50% of the probability mass is going to fit between -1 and 1, right? 2 times a quarter, as Rumer so correctly said. But now if I lift it up, it's going to go between much further, right? So this distribution will be way more spread out than this one, right? This one will have, these drawings are bad, but you can imagine, right? So by lifting up the Riemann sphere, you spread out the uncertainty, right? And of course you do. If you make a higher coupon, the variations in values are going to be much bigger, right? Seriously, right? In absolute dollar terms. In relative, no. But then you have to divide again, and then you're back on your regular Riemann sphere, right? And then suppose you bring the Riemann sphere down, then it's like you're dividing by the gamma's a number smaller than 1, so you get even less of a coupon than $1, right? And then you do by getting the Riemann sphere, you bring it down, all right? And then the probability mass gets very concentrated, okay? You can see that because you always know 50% falls between these two trajectories, right? This is why it's called the Cauchy distribution, because Cauchy, he was the inventor of the Dirac delta, and what he did, he used these Cauchy distributions, and he made them smaller and smaller and smaller. He did it purely mathematically, all right? And this is what he did. He didn't do it with the Riemann sphere, but he just wrote it out analytically. This is why it's called the Cauchy distribution, because he used that, and then he started using it to do his limiting procedures. He was always doing complex numbers, and he didn't have the Riemann sphere. Bernhard Riemann saw that, and he was before Bernhard Riemann, but he did it all somehow in his mind. And he had these residues, and I don't know, he was a clever guy. But he's a little bit too clever. Like, I'm not that clever, so I relate more to a mathematician like Bernhard Riemann, who says, well, I'm not that clever, but if I just look at it on the sphere, this is what it was called, the Riemann sphere, then it becomes simple, and I can do it. I think I said that last week to a student. I said, well, how are you able to do this? And I always say, well, because I wasn't clever. So I had to see these tricks, and then everybody thinks you're clever, but everything is the opposite of what it seems. Okay? So you can see, these are called parameters. Now, the other thing you can do, and I didn't graph that here, is shift it over. Remember we did that as well? So then it's like a rate, now. So it's when the thing, I think when it's a deferred annuity. You have to shift it over, right? So you have to subtract. I forget. Doesn't matter. We did it. Yeah? So you can do that too, and then you take the Riemann sphere and just move it to the right or move it to the left. Okay.
Do something like back to like different. So we took this like shift in the S domain and you take it to the time domain. Then there was something.
I think it's like
it's scaling by some exponent.
Yeah, but I think it's a move over. Wasn't it a move over of the payment?
Yeah, but it's in the time.
Yeah.
Now we have a shift in the
if you have the exponential in the
Yeah.
time domain, then
So
it
that's
becomes
a
a shift in the
discount
frequency
in the
domain, so you already discount the time signal.
Oh, yeah, it was a growth. I had a growth,
For
yeah.
example, if you take into account inflation for some reason and then calculate valuation,
that's right.
the valuation in the
Yeah.
process.
So you add a trend on this thing, right? So that's, sorry, I got the two confused, right? So you see I'm not that clever. Emil, he saw it. All you do here, this is sort of a trend that you got. You got to detrend it. You subtract it, right? Or add it by detrending it. And this thing is then your payment. Then I would do gamma times S plus mu divided by gamma would be a little bit better, right? So you first detrend it with this thing, and then, or you can also do this, of course, gamma S plus mu, and then this mu is a detrending not in the discount rate, but in, now the discount rate times the coupon you're actually getting, Either way, this is what is called the mode and the spread parameter of the Cauchy distribution, right? So you'll see that I write Cauchy 0, 1. Now you will have a Cauchy, I don't know what this is, mu gamma, right? So the way you might write a normal distribution, you might write a normal, something like this. But this is not the mean, this is the mode, right? And this thing, gamma here, is like the spread of 50% of this, the probable interval, okay? This is how statisticians index the Cauchy distribution, and you can see how it corresponds to locations of the Riemann sphere, and if you don't listen to me, but Emil, you can also see where it corresponds to economically in terms of discounting and trending, and you can easily see where it corresponds to, in controls, right? And it's just your usual, if you do this, kind of stuff, All right. So that's an important property, right? So with this, you can kind of get away. There's one more really important property of the Cauchy distribution, and then we'll take a break. And that's this one. So if you have a whole pile of values, and they all follow this simple, they're all perpetuities or trended, upscaled this, right? A whole portfolio of bonds or stocks or who knows what, some fixed income instruments, right? And the total value will be the sum of the individual values. That was the whole point of the Laplace transform, right? That it's linear, all right? Now I ask you, what is the distribution of that whole portfolio? If all these follow this simple Cauchy model that is a perpetuity or something that is, Now in general, what's the distribution of a sum of random variables? Does anybody remember that? How do you calculate that? Can you just sum the distributions? No, you can't, because you'll get probably mass 2. So that won't work either, right? If you just sum two densities, yeah, but you have to convolve the probability density, right? You remember that? And then if they are independent, maybe you can multiply them and yeah, now. Okay. So if you just start adding distributions, that's kind of silly because one of them adds to, integrates out to 1, the other one does 2. You add them, you're going to get 2. Probably it all doesn't work, right? So normally you would, convolve them, I don't know. Somewhere you should remember this or not, And when they're independent, then it gets a little easier, right? See, if you have two random variables and they're dependent, you add the uncertainty in x plus 2x. And how can that be a sum? The one just depends on the other, and you just have a 3x, just multiply everything by 3, and you have the same distribution. So then you have total dependence, and then you can have independence, and huh? All right, it's a hairy field. And did you guys get a course on probability and statistics?
Yeah.
One. And somewhere in there they must have done this.
Well, it's in formal indication on formal.
Yeah, but if you take the sum in the Kolmar filter, if you take the sum, you got to be a little bit careful that they're independent.
There's some rule for it.
Right.
Yeah, at least you can find it.
But you're never adding distributions. In the independence, you're multiplying, right? Because if you look at the Venn diagram, what's the chance of this and that occur?
Random variables, and there's some. I don't recall.
Like whatever. Right, they got all kinds of rules, you know. Huh? All right. Now, the point is there's a couple of distributions that the sum is the same as if independent variance is the same as the thing itself. And the most famous of these is the Gaussian model. And in fact, the Gaussian model emerges because if you take non-Gaussians and you sum enough of them, and then I would also divide by n the number of them, right? This thing will converge to a Gaussian. That's called the central limit theorem. You may know that. So you name a whole pile of independent measurements, some distribution, some weird ass thing, right? Huh? And you look at their average, it will converge by the central limit theorem to a Gaussian, right? You guys remember that kind of, huh? Okay. So the Gaussian, if you plug them in to begin with, of course it's going to converge, but you got tons of them that do, but not all, right? And if you look at these proofs, they always require that the moments are finite, you know. I don't want to go into it. So there are other distributions that are called stable distributions that no matter how many of them you add, you get the thing, and they will not obey the central limit theorem. And the Cauchy is one of them. Okay? Proof is, again, elementary in many ways, even with Riemann sphere, but I just want to name it. So you see, this thing is just great because that's what we want to do. We want to add these values because we construct portfolios. And we don't want to have complicated distributions when we have 3 of them and only can you look at infinite, you know. But then you see also what goes wrong for the central limit theorem, because if you take millions of them and you average them, you're going to get a Cauchy distribution, and you won't get a normal, so the central limit theorem won't apply, all right? You follow that? Central limit thing, it says that it will converge to a normal distribution. This is usually the motivation taken behind it. They say, okay, this noise consists of lots of little elements, so we'll assume that, you know, we have lots of them, so we're looking at the average effect, so it has to be by the central limit theorem. You'll see sometimes by the central limit theorem in the text. Yeah, but did you check the conditions? And you got to be careful because a very natural distribution is the Cauchy distribution, and it won't happen. So a lot of these models, like Black-Scholes and this, they all make an appeal to that, and they're always wrong. And then they have crashes, so the whole hedge fund will lose all their money because a tail event occurs, because and then they assumed all this thing with a lot of mathematics, and it's wrong, okay? So it's a stable distribution. That's just a name that Levy gave to this. This is some mathematician doing this stuff. For our purposes, what's important is that the type of operations that we're looking at least the first order ones and some of these, the Cauchy class is closed. We don't run out of it, you know? So the model will help us. And we can use these parameters to say, okay, and this is the spread, and this is this, you know, all right? Huh? So it's very nice. So you see these properties are phenomenal. I mean, we can just start making progress with this as a basis, okay? So that's what I want to do after the break, and then talk about losses. and then go to how we can explain these kind of things. And then at the end, I wanted to do Bayesian inference, so we may not get to that, but let's see how far we come. All right, well, let's go and take a break. So will you put the recording on pause, or shall I?
Do it.
Okay, let's continue. So here's where we left off. We derived our Cauchy distribution on the discount rate, and we showed that that's really what we mean by a random discount rate. And what we're doing now is just trying to calculating what that means for value. If you look at value, the way we've done it is just a Laplace transform of the signal. Okay, in this case, we use a want or a force. And here are no real answers except just some tools that you can use and some nice properties and some understanding. And also I made the link with the work we did earlier that you see all these transformations of the Laplace transforms can be viewed as elementary motions of the Riemann sphere. So flips, rotations, and shifts up and down for the scaling and right and left for the offsets, okay, in the frequency domain, which corresponds to precisely the inverse in the time domain. All right? Just because of the way the exponent of the log works. Okay. So what did I want to do there? Oh, yes. What I want to do now is make the next step, look at the loss function. Now, remember the loss function, right? We took the value, we subtracted, and we expanded it around the Taylor series or some point r. We subtracted it and divided by the value at r, and then we defined this thing called the loss function. And the loss function gives us our risk exposure. That's why I call it in percent, right? And what you see is that you kind of get a Taylor series without, of course, the zeroth term, because that's exactly what we subtracted, because we're only looking at how far the value deviates from the value at this point r, where we are currently, or what is our reference value, okay? And we see there's a linear thing that goes with the duration, and duration is just a number here. I looked at my previous slides, and there was a nasty spelling error where I had an S here, no, right? This is evaluated at r, right? It's a Taylor series. So this is the linear term in S, this is the quadratic term in S, and this is, and then so it goes on, okay? Now I ask you, what is the uncertainty in the loss? Wow. You shouldn't do that anymore. It's easy, right? So if I have a distribution on S, I can, at least if I leave this part out for the moment, it's totally trivial, right? Because it's just linear in S, right? I shift my probability distribution over a little bit and I multiply it by, right? Okay, nothing going on, right? So I have some distribution and now I rescale the x-axis, you know, so I do this or that, right? Okay, and then I just move it over a little bit, right? That's all I did here, right? So super simple transformation. Obviously, this thing will be Cauchy then, right? Because this thing is Cauchy, and this is the most trivial thing. And that tells you immediately why duration is such a nice way to measure risk, right? So you just take whatever distribution you have on your discount rate, preferably a Cauchy, but could be anything, so whatever you chose. I just think Cauchy is nice because it represents randomness, and you multiply it by this factor, you know, that's gonna like tell you how peaked it is, right? Because you're scaling this thing, huh? And then this other thing is irrelevant, okay? Because that's telling you around what you called your reference. So this thing truly is what I would say is a risk factor, okay? Easy, huh? And this explains its use. Why it's so intuitive. It's just the easiest thing you can do. Okay? Now, in a very advanced text, they'll look at the at the second order term, and they're called the convexity. So again, this is just a number. I is also just a number, right? But now we have to look at the distribution of S squared, right? Ignore the fact that it's moved over a little bit. Now, is that going to be Cauchy? No. There's no way. Because if S is a negative number already, I'm going to get something positive, right? Well, this looks more like what would be called the volatility or something. You know, it's like it goes with the square. Anyway, how do you calculate the distribution of S squared? It's actually kind of easy. This is the distribution of S, and this is the Jacobian of the map, right? I just do the derivative of S squared and do 1 over. I still have a pi, so this is it. And this is the distribution. All right? Okay? So you see, it's all peaked around here, and it drops off pretty dramatically, okay? So this also tells you why you can, for some applications, for small variations in S, you can kind of ignore this, because it doesn't happen that, you know, it doesn't have much of an impact, okay? And you can walk yourself through all these other terms, and you'll see they'll get more and more peaked just because this thing starts, you know, this Jacobian is going to come down more and more and more here. You'll get something to the n minus 1 or something, right? And it's more and more peaked. So you're more and more certain about what that part is going to be. So you can imagine, if you look at this risk metric from this perspective, that indeed duration is a really good way to use as a risk factor, right? A way of measuring the risk, or risk measure, or risk metric. You see everything in the literature, all right? So I just wanted to feed this back. Last time I said, well, it's a way of doing risk, and you can imagine that if this thing moves, I think it's going to move a lot, and blah, 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 because it's the derivative of the value with the interest rate or with the discount rate, so that's big. Now, oh, you got big, you know. This is what, just explicitly in terms of it. So the relationship between risk factors and the risk itself, okay, as exemplified by the uncertainty in the distribution over the losses. Now, I mean, what's the difference between uncertainty and risk? And that really, the difference is that usually when people talk about risk, they mean one number, like the risk is 5, or risk is I don't know what, right? When they talk about uncertainty, they mean a whole distribution. Now, whole distributions are just hard to report upon, right? Because it's an infinite number of numbers, right? So what you try to do is encapsulate it in one number, and you see here the attempt to do so, right, with this duration. Of course, you can never really, for all purposes. This is only for relatively small things, because you know that, you know, only there you'll have high values, okay? So otherwise, you'll have to look at other things. So risk metrics or measures are always relative a little bit to the problem you're solving. Otherwise, as an economic engineer, you have the entire distribution, so you can calculate any risk metric you would like, okay? So this is precisely what I want to do now in the next 15 minutes, just go through a couple of the existing ones, well, actually only through one, and that's called value at risk. And this one you see used all over the place. This is the most popular. And it's a rather mysterious thing. It's also been blamed for being overly simple. So I think it's David Einhorn. David Einhorn is a big hedge fund manager with billions of dollars and all of that. He called it like an airbag that always works, like an airbag in your car that always works except when you're in an accident. So what happens is, in these quantitative analysts, and they're at these Wall Street firms, and they sit and they calculate all kinds of stuff. And one of the things they calculate is the risk in a portfolio, because the companies have to do risk management. And then they use all these tools and they come up with a number. And before the crash, they would use a lot this value at risk number. I think Morgan Stanley, but I get them more confused, was really big at it and had a huge site, okay? And then they use that to construct these subprime things and other things to say, okay, the risk is relatively low. It's so many AA grade because the value at risk is this and this. Of course, the whole thing went pear-shaped and bankrupt, and then everybody says, well, how come if the risk is so small, this is a 1 in a gazillion type of event, how come this is happening now a couple of times, you know? Huh? So it hasn't been working very well, but anyway, let's just look what it is and see how easy it is for us to calculate what it is, how they should use it, and how we would do it, right? So what they do is, here is Investopedia, and they look at the returns. So that's the transfer function, right? And these guys, this is from Wikipedia, and they look at the profit and loss. So that's more the R function that I have there, the loss, right? So you see already, they don't really agree when they look at that. So is this a transfer function, or is this profit and loss function? But no matter, right? This is number one. We can kind of fit both. Well, what are you really looking at? Well, that's the first step to do. And when they do that, this guy is looking at the QQQ, the triple Q. This is the NASDAQ is some kind of stock index, and you take the first 100, the biggest 100, and you just track the prices and the drawdowns and the fluctuations, you know. I assume you have some, you know, you can just plot the returns of this thing. And this is what you see, and then they fit this distribution. So you see what they do. This thing goes down pretty fast. And of course, they can't go below 0. So you see this is also has to be crunched up a little bit here. And then they say, well, what is the value at risk? They'll say, well, this is so this is 0 here. This is the profits. So they run like this, and these are the losses. And they'll look at this. This is at this point, there's only a 5% chance that your losses will be bigger than this amount. Okay? That's what this graph says. Okay? Oh, this is the frequency, sorry.
They say value at risk 5% or something.
Right.
The argument of the percent, and then says which amount.
That's right.
That.
Yeah, that's what they do here. Oh yeah, this is what he tries to explain. I always get confused in these explanations, but that's precisely right what Emil said. Here you have a similar thing. Line at 0 minus 0.28 means 5% value at risk is, so here you go. So this is 5%. So this is the 5% quantile or fractile. And then you calculate what this number is at which this is. And that's called the value at risk. So you assume the 5%, and then you start figuring out how big the losses are. Okay. Now suppose you have this way too tiny, this tail, and you know, now you're gonna underestimate that severely, right? Now these are difficult calculations. You can imagine how do you get it, but the Cauchy kind of gives you an immediate answer, because the quantiles are just easy to calculate. Now, these are the quantiles of the standard Cauchy. You will have to, if you have a portfolio, you have to kind of figure out what you have, and then you'll get the true 5% fractile out of here, okay? The other thing they wrestle with is the period, you see. So the statistics, how were they calculated? They were calculated over a period of 1 day or 5 years or whatever. So they'll fix a period. So it's, and they'll say the 2-year value at risk at 5% is equal to whatever, 0.82. And so, you know, evaluated over the last 10 years, we see we have a 5% chance of losing more than 82% of our the value of our portfolio. Now, this is just what they do. With the Cauchy distribution, you can derive what is the right value distribution or the right loss distribution, okay? And you can just calculate what it's supposed to be. But then I think to myself, well, why? Why not just keep that quantile function that I have over there? You just plug in the quantile you want, out it comes, okay? And The other thing it gets criticized for is that the tails are too thin. So these things, and then you'll see this is exactly what the Cauchy has to offer, because they all use Gaussian fitting for this. The whole pile of stuff you can, A, you can understand what it means theoretically, and B, you can see what it means in your model and how to do it, all right? So I don't want to say too much about this because a lot is said and books are written. This guy, I mentioned him before, Nassim Taleb, he's made a whole career. He used to be a quant, one of these guys who used to do that. Then he noticed he could make more money by writing books on how nonsense it is that they're doing this. And he became very famous by saying none of statistics works. And he's got the point, it doesn't work. So he's written 3 books and he's testified in Congress. And people ask him to speak at very fancy locations. And he repeats his story. The problem I find is not that he is wrong. And most people say he's kind of insulting. That part I like. But he doesn't suggest anything constructive. Okay? He will just say, look, it doesn't work. And you guys have hired all these fancy mathematicians and stuff. And you're just deceiving the public, okay? And you're just causing these crashes. He's got some great quotes. I always forget them, and then I decided to remember them for this lecture, and now I've forgotten them. So as the lecture is over, I'll remember some of these quotes, but they're great. You should look them up. Okay, but that's enough for that. That's more of the practical tradition of finance, and then you have guys in mathematics departments. We have one here, that one is more practical maybe, but lots of them, they do a lot of this kind of stuff, value of risk. And they have things that they call risk measures. And the way they will proceed is they will list a bunch of desiderata, things that they want from their risk metric, and then they'll start deriving what mathematical formulas will be consistent with that, okay? This is how these guys proceed. So they'll say, okay, we need some risk measure. So what we want is it is a function of this loss. So usually they think of it as a loss or something else. And when you make no losses, then the risk is 0. So, now. And then they go on, right? Then if the value of one portfolio is always below that of another, right, as a function of S, right? Then the risk should be less. And then they move on. Yeah, that's clear, right? Then subadditivity. This one is interesting. So you see that the risks are subadditive. Now you see kind of the right answer for this is, of course, in the stability of the Cauchy distribution, that if you have the sum of two Cauchys, you can actually calculate what that other thing is. And the reason they do this as mine is because you have this thing called diversification. So the idea is you have multiple stocks in your portfolio, the total risk has to go down. So this thing has to go down. Now what you will see, if you take an average of 2 Cauchy distributions, it will still be Cauchy, but the parameters you will see are more concentrated. Okay, so the probable interval will get much tighter as you look at these averages, okay? And a portfolio is sort of an average. Instead of putting all your eggs in one basket, you have some in one, another. It won't go to a normal, but nevertheless, it will tend to tighten up, right? You can just specifically calculate it. So this is reasonable, because anything based on that will, of course, give this. Then they do this kind of stuff, right? So they multiply it by a gamma. Sure. We've already done that. We've multiplied S by gamma, and you can just see what happens, right? So you can just calculate it, and you will see, indeed, if you look at those parameters, it's basically multiplying the distribution by this gamma. It's just lift up the Riemann sphere, and then you multiply that. Oh, that's nice. Translation, and you just shift it around, right? So you shift them an amount of value around. This is, to me, it's interesting when these are very, this is a subject is highly involved with all kinds of proof, and they usually start off, assume a probability space and a Lebesgue measurable functions and a Borel set and all of this, blah, 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 blah. It gets kind of hairy, and then a couple of these things, and then they start proving stuff, right? So the way to attack these things is don't worry too much about all the measurable stuff because we just have a Laplace transform. So all these conditions are satisfied, no problem, right? And then just kind of figure out what the conditions mean and which ones you can drop, because they drop some and combine them in something else, which is, this one is quite popular, entropic risk measure. So they'll look at the expectation of this thing. Why did I put an X here? V. And, well, I know why I put an X, because I'm copying what they are doing and trying to translate it for what I do, and then I forget to translate at certain stops, right? So this is not my formula. But you can see if you have this expectation is some kind of, you do it against this probability distribution that you have for your value or whatever you plug in here, right? And then you can have this. This looks like a moment generating function, by the way. This thing, and then you can take the log, and this looks more like a partition function. This one is interesting because it's the exponential utility function. It's the one you can use when you do Feynman path integrals and things like that. So, but I'm just here. My intention of this slide is not so much to go through all of this. That's more for a thesis or somebody who's really interested. My intention here is just to show you that when you start off with this economic engineering basis, you add a little bit of randomness in your discount rate, that you basically can start doing all the things that you've got the connection to what they're doing, okay? And then you can move with your thesis work, or, then you got the connection. This is what we search, that little connection. And then boom, there you move. All right, so forget about it right now. So we had a nice presentation from the Rabobank, and they talked about what they were doing, and they identified 4 types of risk: market risk, credit risk, liquidity risk, operational risk. So just to say that I put a distribution on the discount rate doesn't mean that I have all risk topics, right? This is just a specific one, okay? Only interest rate risk. We still have to look at the imaginary component of the Laplace transform. There's lots of time domain risk too, there's not necessarily in the frequency domain, right? But nevertheless, if you look at this slide, you'll see here an IRR, so you're in good shape. You can do that one, right? This is his credit risk. This is what he does. But the credit, you can think of the fact that if his credit is low, that you'll discount any loans that you have outstanding to him higher, because the chances of losing are just bigger. So you may shift the distribution of your discounts, given this prior information, using some kind of Bayesian updating, which I will talk to about later. So you can attack this problem as well, and you see that they have this probability of default. That's probably best translated into a distribution over what the exact discount rate is. If you choose to do it this way, the exposure, you can look at these exposure factors like duration or convexity, right? If you expand it in the Taylor series, and then you can look at certain values, I guess. Again, it's not my intention with this slide to say how these problems can be solved. My intention is more to indicate how we can take, because you see he has a distribution here, and this means the inverse of a normal, and it's kind of built in, and this is kind of very small lettering compared to this. So you see, this is maybe the point where we can, and then he just draws this. And there's a lot of nice terminology, but one opportunity is to be a little bit more clear what this distribution really is and how we can translate his concepts to ours of quantiles and other things. Okay? All right. This is all unreadable. The real slides are available online. This is just there to give you an idea. All right? So that remains 15 minutes. And I may not be, this is a very busy slide, but I do want to I do want to start this off at least. Otherwise, you will just have the feeling that you're just doing a bunch of pushing around of probability distributions and just yeah, being very clever, you know. And this is where I want to dispel that. And I want to introduce the idea of what's called Bayesian statistics. Now, statistics is different than probability theory. Up to now, we've done pure probability theory. So there wasn't a single data point in sight. We haven't updated anything. We haven't done any statistic, not estimated anything. We've just used our physical laws or economic laws to derive what it should be, the thing that is consistent with the notion of randomness in these for the models that we have right now, okay? So I want to now start doing real statistics, okay? There's again a busy slide. I want to go fast through it, and next lecture we'll go through it if there is a need to do so. Now, in Bayesian statistics, there is a very famous problem. It's called the lighthouse problem. Has anybody heard of this? You've heard of it, Koen? Anybody else? This is the problem. So you have here's the shore, right? The S is for shore now. And this is a lighthouse, right? So there's a light. And it's sending pulses, okay? And it's turning. You know how a lighthouse works? It turns and it's sending out pulses. And you're sitting at the shore with all these photo detectors and you detect the pulse. You can just look at the shore and you see, it lit that part up. Well, you start doing that, right? So you can then see, if you do that fast with a lot of light, you can sort of see a distribution of intensity of light, of light energy, right? And some parts of the shore are going to be lit up and others are going to be relatively darker. I mean, that's obvious. Right? So it's obvious this part is going to be the lightest, and this part is going to be, the further you go, the darker it is, because it's going over here and scooting away like that, okay? So should it come as a surprise that this distribution is Cauchy? No, right? There's always just done. This is another way of looking at stereographic projection, right? So that's, with our work, almost immediate, right? So what I like about the problem is it's a real problem, and you can see that this is just a writing. I mean, come on, right? And this is very, very natural. Okay? But now the lighthouse problem goes a little bit further. So you remember, now we have a lighthouse here, you know, here's this lighthouse, right? But remember, this is our old discount rate, and this was our gamma parameter, right? Our scaling parameter. Yeah, this is the payment. Now, suppose that you don't know where this lighthouse is. See, we assume that we know that the coupon is going to be this, but suppose you don't know that. You just know you have a bond, but you don't know what the coupon is. You start measuring, right? You know, and what you can do is you start measuring all these discount rates, you know, and seeing, you know, what you can infer from the value of the coupon, for instance. That's statistic. You could also assume that you have this shift over, that you have a trend that you don't know what it is, right? And then you can make measurements because you'll see if this thing is shifted over, the distribution will be over there, right? So you can start making measurements of the discount rate, you know, and seeing if you can see what the trend is in your data, okay? The way to do that is through Bayesian inference. And this is where it gets nice, because you got a model. You can actually use Bayesian inference. Now, what I'm going to do is go through this quite fast because there's a lot of terminology. You all know it, but to see it all applied can be quite a challenge. But I just want to do this and then end the lecture, and then we'll go through it more carefully. So what is the problem? You want to find out what the value of what the distribution of your value is after you saw all these measurements, right? This is where we want to go to. Now, how do we do that? Right? We don't even know what this distribution is. We only know that if we know how far the lighthouse is out or how far it's shifted to the right, I left this thing out of the problem, then we do know what it is. This thing is a Cauchy distribution. So what should this distribution of the value be? Well, you first condition on what you know, and then you multiply by the chances of that thing actually being there. And then you add them all up, and then you have that distribution. This is just conditional distribution, right? So this is where you're in business, you see, because this thing, although you have no idea what it is, this one you know. So now the whole problem is simpler. You just have to find out what this distribution is, all right? You have to specify this one. Now, you can say this thing cannot be negative. You can make, there are assumptions you can make, and they're called conjugate price. I don't want to talk about that right now. I'll talk about that later. But I'm just assuming you can do that. For all I care, you put some uniform on it or something. Huh? But whatever you do, you're going to take these measurements. So you don't want to know what the probability distribution of your volume is right now a priori, but you want to know it after you've taken these measurements. So you take n of these measurements. So you want to calculate this conditional distribution. They're named, this is the prior predictive and this is the posterior predictive. And they're called predictive because they predict the actual sample, the observation itself, okay? So then I still have, given that I know the parameters, I still know that this is a Cauchy, so that's not going to change, right? But this thing is definitely going to change. And that thing is the one I'm after because I need to know what is the distribution over where this lighthouse is, all right? And that thing will get more and more certain as I take more samples, okay? Now, to calculate this is called the posterior distribution. And this is called the prior distribution. So you have to distinguish that from the predictive. This is about the parameters, and this is about the actual values, the thing you're interested in, all right? There's a lot of moving parts here, but they should all be familiar. It's just that it takes a while to put them in the right thing. Now, how do you go from here to there? Well, you use this thing called Bayes' theorem, right? So you know that the conditional distribution of gamma, given that, you just flip them around, times that, and then you divide by probability. So I put this proportional sign because you know this. Well, this is your good old Bayesian formula, right? Everybody knows this. So you see, but again, this one you know. So you're in good shape. You can just calculate what this product is, and you will see that if you take enough, this thing is going to dominate pretty clearly, and no matter, unless you did something crazy here, this thing will start converging to quite a peak distribution, you know, that starts looking very similar to this likelihood function. So then you plug that in here, and then you can find this thing. That's how it works. Now, this is just a bunch of math. The whole thing that makes this work is that we know this guy from our consideration, right? Now, the normal applications of Bayes' theorem, this thing's come falling out of the air, this thing comes falling out of the air, everything comes falling out of thin air, okay? Here, we're in great shape because our likelihood, the thing we use to process the data, doesn't come falling out of the air. That one we have derived, okay? So we still have to derive this thing. So there are ways of doing that, and maybe I'll talk about that, maybe I won't. But that's not so important because if you take enough measurements, you know, or statisticians will call this a sample, right? But it's really measurement, right? Of observation in economics. You know, this thing will converge, you know, to a very narrow distribution, and you can just calculate all this stuff. All right? This is how you can use data. You can use data on any parameter, so also on the shift parameter, And this is the mechanism. So it's a fully Bayesian, and this is also what's called operational Bayesian. There's like a Bayesian method where it actually, you always see the same thing. Like this distribution can be anything, or this can be anything. But what you do is you say the physics of the problem limits it to cases where these are sort of mixtures of these Cauchy distributions here, okay? So I know a lot already because this is some huge multivariate distribution. All I need to know is the distribution on this prior parameter, okay? And then I know that if I have enough data, I can't be too crazy about this, you know, that I assign probability 0 to huge intervals, you know, huh? And then I can always find the right thing. So it's kind of the key of Bayesian inference. The other big thing here is just, why did I insist on using these Greek letters rather than the letters we had before? That would help me remind what they all represent and that this is a frequency shift and all of this stuff. It's because that's what statisticians do. Now, they have an approach where you just have some data points, that's what they call samples, and you can kind of know what those are, right? There's just some length or a height of a Canadian or something like that. And then they have a model, statistical model, and then all of a sudden, it boils down to finding the parameters of this model. And all of a sudden, you'll lose touch with what these things are. So you'll say, well, this is the mu, and this is the sigma square, and this is the kurtosis. Yeah, there's a kappa they use for that. And they have all these parameters, and they're purely abstract. They have no physical meaning, no economic meaning, no nothing, right? And then you let this whole apparatus go loose, and sure, you can do a lot of math and a lot of statistics, but you're never quite sure what it is you're doing, right? Now, what's different here is not only that we know what the likelihood is, so we can use this Bayesian convergence, but that we know at all times what the economic or physical meaning is of all these crazy Greek letters here, right? This is what makes it applicable. And this is a huge distinction from all these var problems and this, where you say, well, I assume the model is out of this parametric class, and it has a such parameter and a so parameter, and now I'm going to estimate it using those methods, okay? This is a very big distinction, okay? So this was quite a journey. So we went from knowing nothing to knowing what knowing nothing means, like randomness, and also how to build the models, how to think about these models in the context of the Laplace transform and present values, and then how to use measurements to update our models, okay? So my time is up. I want to stop right here, and I hope to see you all next week when we continue this topic of infinite interest, the use of the Laplace transform in calculating value. Okay.